Hello, I am Sara Abu Zayed. I am a bachelor student in physics at Birzeit University in Palestine and now writing my thesis here at Yulish Research Center. I have a task in one of the projects at the Central Institute for Engineering and Technology, ZEA-1, which fabricates scientific and technical equipment, instrument, processes that are not commercially available. We cannot find it on the market. At ZEA-1, you can find staff of engineers, physicists, technicians, material scientists, mathematicians, manufacturing experts that they are working on the project from the idea to the best results of the products and systems. So with this stuff, you can find that they are working with, at first with the other institute at the Forschungszentrum Jülich, and also for another researchers in Germany or abroad, like research at universities or industrial partners. For example, at ZEA-1, they are working for equipment and instrumentation for plant and soil investigations. And they also work with medical scientists or medical experts on combining various imaging techniques for medical use, but these imaging techniques can be also used for environmental research, like we can use it for determining the rate growth, the growth of roots inside the soil without, with no need to. We can use these imaging techniques when the roots are in the soil and no need to take it off from the soil. So this is good. This is good attempt. But now any project, or often a project begins with an attempt to answer a scientific question. So throughout the history, the question about the origin and nature of matter have always found a big interest. But answers started with on the macroscopic levels down to molecules, atoms, and now the smallest known particles are quarks and leptons. But at the scale of the smallest known particles, the quarks, many questions are still open, and some phenomena related to this cannot be accessed by the theory and must be studied by experiment. So, for this, Helmholtz Center for Heavy Ion Research, GSI, in Darmstadt, Germany, is building a new facility for such experiments. They are building the facility for antiproton and ion research, FAIR. And one of these experiments is called the PANDA experiment. PANDA experiment, ZEA-1 also works with GSI on it. PANDA will help particle physics scientists to answer questions about the nature of constituents of matter at this small scale by providing a high precision in spectroscopy of hadronic systems produced by proton-antiproton annihilation. So they will collide on proton and antiproton annihilation and then make a high precise measurements on it. So we can see here the FAIR facility at GSI, and this is the PANDA experiment and the PANDA detector equipment. What I am interested in is located around the interaction point for the proton and antiproton annihilation. This part, what I am interested in. It's called the microvertex detector, and it's the detecting system directly surrounding the interaction point. And it's made of silicon pixel and silicon strip sensors. And for my project, what I am interested in is the carrier structure that that carries the silicon sensors. The stave is made of carbon fiber and carbon foam for reasons related to the high precision for what PANDA want to give us in detecting the antiproton and proton annihilation. But the stave, it's okay. The stave carries the silicon sensors, but also carries the front end electronics. As we can see that the strip sensor will be in this part, and it's made of carbon fiber at the surface and carbon foam at this part, and this part has the front end electronics like the readout chip that will collect the data from the sensors, and also it has a cooling pipe between the chips in the carbon foam. As I said, that the PANDA has to be at high level of precision. So the detector systems require a high degree of geometric precision. We are talking about microns. So the position of the sensors have to be stable during the lifetime of the system. It's nearly 10 years of operation. But the electronics will produce heat, and this heat may affect the stave material, the carbon, and make some deformation in it. So if the deformation happened, the position of sensors will be changed, but we need a high degree of precision. So we have to know how much the heat will affect the structure of the stave. So this time we have to think about how to measure this deformation. We are talking about microns, and we need to measure the whole stave at each point in all directions, X, Y, and Z. So ruler, no, not precise enough, and micrometer, it's too small for the whole stave. So we have to think about something new and something suitable. One of the modern techniques is called digital image correlation. So to know why it's suitable and why we can use it, we have to know about it. So the digital image correlation is a camera-based technique for measurements of deformation on object surfaces. So only we need cameras. So no need to touch it, and the cameras can see everything, can see at small scales, so we can use it in this case. And the images from the cameras are automatically evaluated by algorithms. So now the digital image correlation is independent of the scale. We can use it at macroscopic scales and in small scales. So this is a good point for it. And the results quality will depend on the camera's properties. The better the cameras we have, the better results, and something called quality of the speckle pattern. So, but what is this speckle pattern? I will explain this after explaining this what we can see. To measure the deformation of an object, we need the object itself, of course, and we need a light source, good light source for the cameras, and the cameras we will use. These cameras will see the object, have to see the object, and it's connected to a software that will have these algorithms to evaluate the images. But I mentioned that we need quality of speckle pattern. When the cameras take the photos, what the software is doing, the software will take the photo, the first image, we call it the reference image, and then split it into small subsets or facets, it's called facets, and determine what are points inside this facet, and then compare it with the next images. It can determine what happened to the points inside this facet. But if all the surface has the same pattern, so the software cannot recognize in which area he is. So we need the surface to be unique and random. And maybe we can find this, but we can also we can spray it. We can make the object surface, we can spray it by white and then spray it by points from a black spray. So we will have a unique pattern and random pattern, so the software can recognize in which area he is when he split the surface into small facets. So now we understood what is this digital image correlation, and this is the time to think how I can use it to determine or studying the effect of the heat on the stave. So the first idea was to have a complete stave. This is a complete stave only made of carbon fiber and carbon foam with the cooling pipe inside it without the sensors at the first step. And I bring the cameras in a good position that it can see the whole stave, and then I have white light source, and I have also a thermographic camera. I will explain why we need this. So I put the setup, the cameras, the stave, and the white light source. Why I need the cooling pipe in it? The first idea was to put a warm water through this cooling pipe. It's for cooling, but we will use it to heat up the stave and see what will happen. So I used this device to heat the water. I raised the temperature from 20 to 50 Celsius in steps, and at each step I used the thermographic camera, and this is what the thermographic can see. Here we can see that the stave is speckled, but the thermographic camera can see how the heat is distributed in the material. So at each step I see what the values are for the temperature on this area and this area and this area and this area. And when I have a stable thermal conditions, like the temperature is not increasing too much, or so I take some images or some photos from the digital image correlation, cameras. And now I calculated, the algorithms calculated what happened to the stave during the heating process. This is what the software can see, and because I fixed the stave, but only it was free in one direction to move, I studied what happened in one direction, but we are planning to study the other directions. I took a line come from the beginning until the end and see what happened to this line. This line, the length of this line increased at every step, and so I plot the temperature, the length versus the temperatures, and we found that we have a 13 microns that the length increased. So this is an indication that something will happen to the stave, but we have to be more precise. So we are thinking about more ideas in the future, but I started not so early with this. So for next steps, we are planning to have the complete stave, because this will be more precise if you have the sensors and have the front-end electronics. And maybe we can use resistors to heat up the stave, so the distribution of heat was uniform from the cooling, the water pipe, but maybe from the resistors it will not be uniform, so we can determine more precisely how what will happen. And also, as I said, that the stave will be in the tracking system, the innermost tracking system, so it will we will have a radiation there. So we are also planning to have a radiation from infrared bulb or light source, so we can also study the radiation effect as much as we can. And I hope that everything will be okay. So, but now maybe I have, before ending my my work, I have to thank all people I met here. However, I didn't stay here for a long time, less than a year, but my knowledge increased by many years. And thanks for all people I met here. Thanks for the PGSB coordinator. Thanks for the PGSB advisory committee for this chance. And of course, thanks to my supervisors, Dr. Hazem and Professor Ghalib Natour and Dr. Robert Lohoff and Dr. Eberhard Rosenthal, and special thanks for Dr. Harald Clark and all colleagues I met and I didn't meet, because they were so kind. And this was a nice opportunity, because a lot of stuff, a lot of people, a lot of experts from many fields, and a lot of inspiration every morning when I going in my way to the lab. So I have to thank all people here, and I hope that I can have more opportunity with such a people. And thank you so much.